Good afternoon to everybody and welcome back to this new training webinar of the BIOMAC project. Again, I'm Giulio Poggiaroni from EUBIA, and today we will have another session. This time we will talk about polymers and nanocomposites, and we will discover what it's all about, this very complicated topic with two special guests, who are Professor Daniel Schmidt from LIST, who will provide an overview on the polymer nanocomposites synthesis, characterizations, and applications, and then Professor Dimitrios Bikiaris from the Aristotelis University of Thessaloniki, who will talk about bio-based polymers and nanocomposites. Both of them are, of course, partner of the BIOMAC project, as many of you may know. So again, you're encouraged to use the Q&A box to submit your questions, and we will find time for answering them in between the presentation and at the end. So don't be shy. So without further ado, I will give the floor to Professor Schmidt to start his presentation.
All right, thank you very much, Giulio, and thanks everyone for joining us. I see we have 23 participants right now. So my name is Dan Schmidt. I'm a group leader at the Luxembourg Institute of Science and Technology, and I'm going to talk to you today about polymer nanocomposites and try to give you a little bit of an introduction to these materials, which I've been working with for quite some time. So to start out, one thing I want to spend just a moment on is why I'm speaking about this, what my background is in this area. Figure that might be a useful thing to begin with, just to let you know. So this is where I started my research career effectively. My PhD was in this topic of silicone nanocomposites. This was with a gentleman named Emmanuel Gianellis at Cornell University, who at the time was very well known for clay reinforced materials or polymer clay nanocomposites. And in fact, as a result of that time there, that's my most cited paper. This one is, I think, over 600 citations now. It's one of our review articles from back around that time. Another thing I would point out, because I know that there are people who are interested in the processing side, I wrote a book chapter on nanocomposite processing in the Industry Guide to Polymer Nanocomposites some years back that pretty much summarizes all of my views about how the best way to process these materials is. So I'm going to obviously be relatively brief today, but we can talk about anything you like in more detail in the Q&A without any issue. The other point I'll make is that I've taught a doctoral course on polymer nanocomposites since 2013 when I first developed it. That went on until I left the University of Massachusetts at Lowell, which, as you can see, was where I was faculty. I was faculty in the US for about 14 years before I came to LIST, and I'm actually continuing to teach that course at the University of Luxembourg as well. So it's a pretty comfortable area for me, and as a result, as I say, I'll try to give you a quick intro, but please don't hesitate if you have questions. And I hope also this will not be too much information that a lot of you already know, but I wanted to make sure that I didn't assume too much to begin with. So I think we all know what nano means in terms of the original root of the word. It means billionth, but as we have seen over the past several decades, nano has become a term that doesn't always mean what you think it means. Sometimes it's just used to indicate that something is sort of high tech or cool or something like that. Obviously in science, this is really most meaningful when two criterion are met. The first criterion is that the system that is described as nano should have at least one feature that is less than 100 nanometers in dimension. This is the AUTH definition of what constitutes nano. And the second, and this is the part that people often forget, is that it should do something fundamentally different because it's nano. It's not enough that it's really small. There has to be some fundamental physical difference in the way that material behaves, in the case of nanomaterials, to really be called a nanomaterial in a meaningful sense. So when we come to polymer nanocomposites, of course, a polymer is not a plastic. Polymer is just our macromolecules. When we talk about plastics or formulated systems, we have a lot of other stuff thrown in there. And of course, the nanocomposite is a type of composite. And the implication is that in particular, the reinforcing phase in a nanocomposite should have at least one dimension less than 100 nanometers. So basic definitions, out of the way, right? That's what we're talking about. And I will emphasize also for that reason, sometimes the materials we talk about in the BIOMAC project are borderline in terms of whether they're really nanocomposites or not. If I have cellulose and the diameter of those cellulose whiskers is above 100 nanometers, technically that's not a nanocomposite. And depending on how much we mill our NFCs, sometimes the diameter is above 100, sometimes it's below 100. So we're kind of in a gray area there sometimes, but that's okay. So we should also provide a little bit of historical context here and talk about how new or not new nano is in plastics. You may be aware that carbon black has been used in tires for a very, very long time. And if you look at the particle size of carbon black, it is nano, and it always has been. So you could argue that we've been making polymer nanocomposites ever since we've been making tires, which means over 100 years. The main thing that changed when we speak about the nanotechnology revolution or the nanomaterials revolution or all this development in nanocomposites was not our ability to make the materials, but our ability to know that we had made them. Because at that time, there was no way to characterize these materials to know that we had made nanoparticles or that we were mixing them into rubber. This is fumed silica, another very quote unquote old example of plastics nanotechnology. Fumed silica has been in use since, I want to say, the 1940s at least, for reinforcing silicones. And I remember when I was writing my thesis, I found a really old book on silicones that was written around that time, 1950s maybe. And it was really funny because they basically summed up a lot of what we already need to know, which amounted to, well, yeah, these particles reinforce well, but the smaller they get, the harder they are to disperse. I said, okay, well, they already knew everything you needed to know about nanocomposites in the 1950s, because that's pretty much what we know these days as well. What I also found really funny is they didn't call them nanoparticles at that time, they called them millimicroparticles. So they hadn't started using nano yet. But nonetheless, this has been around for a long time as well. And there's another picture of modern fumed silica, Degussa aerosol, very, very fluffy stuff. So those are nanoparticles. So, okay, why do we care about polymer nanocomposites? What are these? How are they different? So we know what composites are, right? We're talking about mixing or combining two phases or more to give us properties we cannot get in any of those phases individually. And there's lots of different reasons you might do this. When we talk about polymers, it's often a polymer plus a ceramic or a metal. And you might be trying to enhance mechanical properties. You might be trying to alter the physical properties, the thermal, the electrical properties, or even just the cost. When we talk about filled plastics, a lot of times we talk about filler in really that sense of the word. The filler is there to displace the polymer and to make things cheaper. The filler is cheaper than the polymer, and therefore the overall combination of the two has a lower cost. So it's not always anything particularly high tech or sexy. Sometimes it's very basic economics that drives the formation of composites. And in a classical composite, a lot of times you may have heard of the rule of mixtures, and this is a very simple weighted average that can be used to predict various performance characteristics of composites. So you take the properties of phase one and the properties of phase two, and you average them in the right way, and you can predict things like stiffness or electrical or thermal conductivity or thermal expansion coefficient. And this just shows how this can work. There's the rule of mixtures for series and the rule of mixtures for parallel systems. So that's a very, very basic way of determining composite properties. In the case of nanocomposites, there are a couple of differences that I'd like to point out here. So the first difference has to do with the dispersion length scale. So if you imagine that you could be within the nanocomposite looking around, what you would see is you have distances between your particles that are nanometric, and you have many, many nanometer sized particles floating around, as opposed to larger particles that are separated by much larger distances, excuse me. So the dispersion length scale is much, 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 much finer. And this relates to the second point, which is that the interaction length scale is also much finer. And in particular, the particles in the polymer now have similar dimensions. And this is very important because this starts to have implications for what the polymer chains do. And in particular, you can see how this looks in sort of cartoon form over here. We have a layer on any filler particle surface, whether it's a small particle or a large particle, whether it's a fiber or spherical or what have you, of polymer that is not acting normally. And the reason it's not acting normally is because it's been forced to conform to the geometry of this filler particle. Now, this layer is so thin that in a conventional composite, it doesn't really matter, but it doesn't have the same kind of characteristics as the bulk polymer. You tend to see that the first few nanometers of material has non-standard or non-Gaussian chain conformation and non-bulk behavior. And so in a bulk composite, as I mentioned, on the left-hand side, right, versus the nanocomposite on the right-hand side, you can look at these two in cross-section and just say, these are about the same. I have 6% of my area covered in both cases. Well, what's the difference? Well, the difference is this interface, right? This area around each of the particles that is acting differently. In the left-hand case, it's only about 4% of the image. In the right-hand case, it's 45% of the image. So these are not the same. And in particular, a nanocomposite is by definition dominated by this interfacial behavior, this non-bulk polymer at the surface of every one of these particles. So this is really where you start to see interesting and strange and sometimes inconvenient or unexpected behavior in nanocomposites versus conventional composites, is because of these interfacial interactions and what it does to the polymer. We can talk about a lot of different kinds of nanocomposites. We can classify them in many ways. And so the typical classification that I would often use when speaking about these in general would be dimensionality of the particle or the nanofiller in question. So you can talk about spheres, rods or tubes, plates, and even some sort of a three-dimensional network. And of course, we see nanolignin and nanobiochar you could consider to be more or less spherical, right? Our cellulose nanocrystals and cellulose nanofibers are going to be more elongated. I must admit, I spent a long time on the clays, and that's actually where the nanocomposite, let's say the research topic really took off, is in the area of clays. So you will find that I talk a little bit more about them in this talk, just to give you an idea of why it was that people were so interested in them. But a lot of the same arguments that are used to describe the properties of clay nanocomposites can be used more broadly. So let's talk about those systems a little bit more. This work is from Toyota. It was published in '93, but it was actually done in the late '80s. And this is really what inspired everyone to get very interested in these materials. So you have a variety of mechanical properties for polyamide 6 here, and for a polyamide 6 clay nanocomposite here. Now, what is significant about this? The stiffness goes up, not a surprise. The strength goes up, that's not a surprise. The impact strength goes up. This is weird. You don't normally see this. Normally, when you add a rigid, brittle particle to a polymer, you do not see that the impact strength goes up. It normally goes down. The thermal expansion coefficient goes down, the heat distortion temperature goes up, and the water uptake goes down. So the point was that this constellation of properties is one that you definitely do not expect when you put a conventional filler into a polymer. Normally, you expect it to become stiffer but more brittle. You don't really expect that big of a change in the heat distortion temperature. And so overall, this got people very excited, because the conclusion was that, if we make a nanocomposite, we can avoid all the trade-offs that are associated with making conventional composites. And we can just put in this magic pixie dust and everything will be good. Now, I hate to break it to you, but it turned out it was not that simple. But nonetheless, a lot of people got very interested in this field because of these initial results from Toyota. A lot of things were tried, many different matrices, many different nanoparticles. And you do see some really impressive results when you pick the right systems. It's definitely not the magic pixie dust that everyone was hoping for. It doesn't make all polymers better no matter what, but that's what got people excited initially. Another thing that got people excited initially, and this is again to do with the clays, and you'll see in a moment why this is, has to do with barrier properties. And of course, this is relevant in the BIOMAC context as well, because we have a test case that is on packaging materials. So you can see here, we have our conventional composites. So this is polycaprolactone filled with talc. We're looking at water vapor permeability in relative terms versus volume fraction of our inorganic phase. And you can see when you add talc, you get some reductions in permeability, but you really have to add a lot. And when you get up to these kinds of volume fractions here, the material becomes brittle and it's really not usable from the standpoint of its mechanical properties. When you have the nanocomposite, on the other hand, you can get a really significant decrease in permeability with a very small addition of this nanofiller. So why is this? Well, here's why. You have a tortuous path that your permeant must take through the material. And as a consequence of that tortuous path, it takes it a lot longer to get from one side of the material to the other, because it's going around all of these platelets in this case. This is why the clays and things like graphene and metal dichalcogenides and things like that work so well for barrier properties, is if you can get them nicely dispersed, then you create an incredibly long diffusion path. This can also give you improvements in electrical properties as well. We did some work some years back showing that the dielectric breakdown strength increases substantially, because just as with permeates taking a much longer path, electrons to get through this material must take a much longer path as well, because they can't go through the clay platelets. They're nice insulators in this regard. You also see changes in polymer microstructure playing a big role here. So if this is an amorphous material, tortuosity is probably all you have to worry about. But if it's semi-crystalline, the clays and any other nanofiller you like can be very powerful nucleating agents. You can get a complete change in the polymer microstructure. You can even change the preferred crystalline phase, orientation, shape and size of the crystallites, whatever you like. And this has consequences for barrier properties as well. So it's not just the tortuous path argument, although this is a very important phenomenon in any plate-like nanofiller system. But it's also what you do to the polymer microstructure. And another really interesting trick, and I'll mention it later on because this was eventually commercialized, is you combine tortuosity with an active scavenger for whatever it is that you are trying to stop from permeating through your material, and you can get synergy. You can get really high barrier performance, at least for a limited amount of time. So, okay, we have mechanical properties that got people interested. We have barrier properties that got people interested. We can also talk about fire properties. And what you see here again is some work from, well, it's ancient history now for some of you, but nonetheless, some nice work related to nanocomposite fire retardants. And the point is that those barrier properties that I just mentioned can also work when it comes to the degradation of polymers. So when you burn a polymer, you're not really burning the polymer. What you're burning is volatile stuff that's coming out of the polymer. So volatile materials are generated because the polymer is being heated. These volatiles diffuse to the surface, they come out, and in the vapor phase just above the surface of the polymer, that's what's burning. So needless to say, if I can create a permeation barrier that prevents those vapors from coming out so fast, it will be harder to have a very massive fire. And in addition, if my particles, my nanoparticles, are able to form a char layer as the burning continues, this char layer can form a further barrier to the release of additional volatile material. And it doesn't have to be inorganic. If it's a char-forming organic material, this works just fine as well. So the point is that you can use these to reduce the maximum heat output, the peak heat output, or the peak heat release rate in the context of a fire situation, thanks to this initial reduction in permeability coupled with this char formation. And in some cases, you can even see self-extinguishing behavior. In practice, nanofillers alone will not get you what you want for fire properties. A lot of times you have to combine them with other additives, but nonetheless, it does give you a helping hand to reduce the flammability of polymers as well if it's used correctly. And this is an example of this. So the blue is polystyrene, the red is a nanocomposite. You are looking at heat release rate from cone calorimetry versus time. And what you see is that, well, the total amount of heat was probably similar. That's the integration of these curves. But the peak in the heat release rate was much higher in the regular material than in the nanocomposite. And this is important in a fire situation because if you have a very intense fire like this, it's more likely to spread. If you can spread that fire out over a longer period of time, make it less intense, it's less likely to spread. Now, careful observers will also note that the nanocomposite caught fire earlier, which is not good. And that is because the particles have been surface modified with a modifier that comes off and burns a little bit earlier than the polymer itself does. So that is already a hint that things are not always perfect or as you want when you're dealing with these materials. But nonetheless, you can get interesting performance out of them. Okay, so if we talk about the structure of these materials, if we have nanoparticles and they stay aggregated, which is what you're seeing on the left, this is what we would call an immiscible system. It's really going to give you the performance of a conventional composite or conventional filled polymer. In the case of clay platelets, you can get polymer intercalating between the layers without really completely separating them, or you can get complete dispersion. In a lot of other nanoparticles, you don't have this intermediate step here. You really either have dispersed or not dispersed. But the point is that this is what you need to get get a nanocomposite. And while thermodynamics will get you a fair bit of the way, you also have to do the processing right. So the first point here is you need thermodynamic compatibility or you will not get dispersion. I have seen people try to beat these systems into submission by shearing them harder, thinking that this is going to do them good. In the case of large particles, historically, this has worked. In the case of nanoparticles, it really doesn't. And you can appreciate why. The analogy I would always use with my students is, imagine if you're in the middle of an Olympic-sized swimming pool and somebody starts moving the walls back and forth in a shearing manner. Are you going to feel anything? Not much. The point is that these particles are so small that the shear intensity you would need to physically separate them, just based on mechanical force alone, you typically don't see it in any normal process situation. And if you do go to such high shear intensities, you generally start destroying the polymer. So you can't rely on brute force to get dispersion in nanocomposites. You need thermodynamic compatibility. This is essential. This is a model for how this transition occurs to the fully dispersed state. And I will say mixing helps in the sense that mixing will help to even out any composition variations. It will help to move those particles further from one another as they decide that they wish to disperse. But the point is that they have to decide thermodynamically that, yes, I want to be dispersed. And then when that happens, you don't need to really beat them up too much. You don't need really high shear to get good dispersion if dispersion is highly favored from a thermodynamic standpoint. On the other hand, if it is disfavored thermodynamically, you can shear all you want, you will still have poor dispersion. And if by some means you manage to trap the system in a highly dispersed state, and there are ways to do this, I've seen this done before, you can do that. But nonetheless, if you manage, you will find typically that the properties do not follow, in the sense that even though you've managed to get the particles well dispersed, the interfacial characteristics are extremely unfavorable for mechanical reinforcement. And the instant the particles can move again, they will all come back together. And I've seen this happen before. So again, I can't say it enough. You need thermodynamic compatibility. This is why we do surface modification. This is why we look for polymer filler interactions that are positive, because you really need that to make a good nanocomposite. And another point here, which we must not lose sight of, is you cannot get complete dispersion unless you are below the percolation threshold. And so this idea is a very simple one. If you look here at these platelets, I can only put so many randomly oriented platelets into a volume before they start touching one another. And the instant they start touching one another, and I have a continuous path through platelets from one side of the box to the other, that is my percolation threshold. When I hit that threshold, the viscosity of the material will go way up. The mechanical properties will stop improving. Probably they will even start to get worse, because particle-particle contacts typically are mechanically quite weak. And my dispersion state will start to degrade. I will not have individually dispersed particles. In practice, they will probably start to aggregate. There's a really nice paper that I like by Edgar Bazzi at NIST in the US. He published this in '95, and he had a really convenient formula for estimating the percolation threshold as a function of aspect ratio, which is exactly what you're seeing here. Disk-like is over here. So when I say disk-like with an aspect ratio of 0.01, it's not the usual way we think about it, right? What this really means is the thickness is 1/100th of the width. So I would call that a platelet with an aspect ratio of 100:1. Over here, we have the rod-like side. Here we have, for instance, maybe a nanofiber with an aspect ratio of 100:1, where 100 is the length and 1 is the diameter. So the size doesn't matter for percolation threshold. The only thing that matters is the aspect ratio. And what you can appreciate is, as soon as you get high aspect ratio particles, your percolation threshold, this is the log scale, can be extremely low, right? 100:1 will get you a percolation threshold of around 1 volume%. And if you go above that, you're going to get aggregation. So something to keep in mind. Now, in terms of behavior, what else do you see in nanocomposites besides these various properties enhancements? Well, one thing that a lot of people have seen, and I mentioned it here, this is just a fancy way of measuring TG at the molecular level. We have NMR data showing spin relaxation as a function of temperature. When nothing is moving in the polymer, there is no spin relaxation. The intensity of the signal remains high. That is on the left here. And so we are looking now at polystyrene. We're looking at polystyrene that is either nanocomposite in the red or bulk in the blue. And we're looking at a couple of different kinds of polystyrene. It's either been deuterated on the backbone or on the rings. And this allows us to isolate certain parts of the polymer chain and look at its mobility. And the point is, what you can see in the normal polystyrene is you heat, and when you hit TG, things start moving a lot. Enhanced mobility means the signal decays out. You get a little bit of mobility in the D5 case here, probably due to ring flipping below TG, but in general, not much is happening until you hit the TG. In the nanocomposite system, because we are doing weird things at the interface, because the polymer is no longer acting in a normal way, we can see that the TG is smeared out over a broader range of temperatures. And this is another example in a totally different material. A different system. This is another way of looking at this. So this is, again, the spin relaxation experiment in a polystyrene nanocomposite. All you need to know here is that when all the signal is on axis, on this diagonal axis, nothing is moving. And when it's off axis, everything is moving. So you see in pure polystyrene, below TG, nothing is moving. Above TG, everything is moving. When you look at the nanocomposite, you have a population of polymer chains that are moving below TG when they shouldn't be. And you have a population of polymer chains that are moving above TG, or excuse me, that are not moving above TG when they should be. So again, it shows you have a much broader distribution of chain mobilities. Some chains are more mobile than normal. Some chains are less mobile than normal. And this is a consequence of these strange things that happen at the polymer filler interface when you have so much interface in the system. This is another example of this. This is now polysiloxane, just to show you that this doesn't only happen in polystyrene, and just to show you that NMR is not the only way of detecting it. So this is now dielectric relaxation data. It's always hard to look at this because it's inverse temperature. So hotter is to the left now, not to the right. And what you can see is that as you heat up, you have faster relaxation. In bulk PMPS, you hit the TG, here it is, and things start moving quite a bit. In the nanocomposite, you actually see two different relaxation modes. You have something that looks just like your bulk polymer, the green points. So some of the polymer is behaving just like normal, but you also have some polymer that's starting to move early, that's starting to move at a low temperature. That's this blue signal. And you can also see that if I would have continued these curves, they're going to cross at some point, which means that there's also some polymer that's not moving as much as it should, even at high temperature. And again, this has to do with the fact that the polymer chain conformation and the polymer interactions are affected by the presence of all of these nanoparticles and all of their surfaces, all of these interfaces between the polymer and the nanoparticle in the system. A few other key issues. Again, I mentioned it whenever I mentioned barrier properties, but I'll emphasize this point once more. The effects on microstructure are substantial, and this can be to your benefit or to your detriment, depending on what happens. You can change the dominant crystalline phase. So by the way, if I go back to polyamide 6, one of the reasons that those materials work so well is because you changed the kind of crystals you were making, you even changed the crystal structure, and you changed the crystallinity. So everything changed in that system in terms of the microstructure, and it made a huge difference in performance. So the crystalline phase changed, the size of the crystalloids changed, the shape of the crystalloids changed, and the crystallization rate and the amount of crystallinity changed. So if you take advantage of this in a good way, you can really get some very nice properties improvements. It can also really hurt you. I was a part of another project where we were looking at ethylene vinyl alcohol barrier resins. We put clay into them thinking, oh, this will improve the barrier properties. It actually hindered their ability to crystallize. And so even though you got improvements due to this tortuous path argument I showed you before, the reduction in crystallinity effectively counteracted all the improvements, and there was no change in the barrier properties. It didn't help at all. So that's a good example of crystallinity hurting you. And of course, crystallization also makes your material non-transparent typically. So if you want transparent barrier, take care. Mechanical properties depend on dispersion state. To get the maximum benefit in terms of stiffness and mechanical reinforcement with a high aspect ratio filler, you need it to disperse well. The other point is a lot of people spend a lot of time looking at nanoscale dispersion, looking for those individual particles so that they can publish and they can say, look, our dispersion is beautiful, all the particles are nicely separated. I had my students do in our nanocomposite class a nice exercise where I took an SEM picture from the literature, excuse me, TEM. I showed them the picture and I said, okay, the author said that this system is 9% silica. Calculate how many particles you should see in this picture, knowing that the TEM slice is this thick and this wide and this tall. And then tell me if it's okay or not. So they did the calculation. And what you find when you do this calculation is that the picture that was published has 10 times fewer particles than it should. They're well dispersed, but 10% of what you should see. What does that mean? It means there's a giant aggregate right over to the left of that picture that the authors didn't show you. It means that whoever reviewed that paper didn't ask that question, and it means that that's not a representative image. And I see this all the time, all the time. It makes me crazy. The point is that those aggregates can cause you huge problems in terms of impact strength later on. That will be where your material breaks. It won't be in the beautiful area where everything is nicely dispersed. It'll be the giant accident just next door that you didn't show a picture of that kills your material. So micro and macro scale dispersion are just as important as nano. I would say that thermal and barrier properties are less sensitive. You can get high tortuosity even if you have a few aggregates here and there. So from the barrier standpoint, less critical. And in general, in a lot of cases, you see that you get good results in rubber, polar semicrystalline polymers, and epoxies. And the reason for this, when your matrix modulus is very low, it doesn't matter what you put in. You can basically put in dirt. The dirt is more stiff than your matrix, and so you always get some reinforcement. It's much harder to reinforce a stiff matrix. Why polar semicrystalline materials? Well, most of our nanofillers are relatively polar. This is always why we spend so much time surface modifying them. Doesn't matter if it's clay or cellulose or what have you. Everybody wants to get something into polypropylene. It's the worst matrix for making nanocomposites. It may be the most interesting polymer from an industrial standpoint, but it's absolutely terrible for nanocomposite formulations. So this is why the polar systems tend to work better, is because a lot of the polar polymers are inherently compatible with more polar surface chemistries that we see in so many of the nanoparticles we're interested in. And then epoxies, it's a bit special. This is an example of a system where dispersion can be driven by chemical reactions with the particles themselves. And I won't go into detail there, but if you really want to know about that, you can ask, or you can ask Kostas, because he's an expert in this area. He has some really nice papers from back when he was in this field as well. Commercial applications, let's talk about that very briefly. There are a number. This is an example where nanocomposites were used to give you gas barrier in tennis balls so they would stay bouncy longer. This is a couple of examples where these materials were used in packaging resins to improve barrier performance. A bunch of automotive applications for improving impact strength, surface quality, dimensional stability, and reducing cycle times. Because these act as nucleating agents, you can reduce the cycle times in injection molding. And by the way, one other thing I'll mention here, very interesting, the Honeywell folks combined an active oxygen scavenger with clay. And when they did that, they were able to get a plastic that had the same oxygen barrier properties as glass for 6 months. After 6 months, the oxygen scavenger is consumed. But since the shelf life of the beer is anyway short enough and people will buy it fast enough, it doesn't matter. So that's a good way to make a plastic beer bottle. And then recently, Boston Scientific made polyamide nanocomposites for their catheters because of the mechanical enhancements they get in the performance of those materials. So there's a lot of commercial applications for these. We don't always see them advertised as nano, but they're out there. And to show you that this is the case also, I went and updated my market survey, because I always do this for the students whenever I'm presenting, just to show that this is not simply an academic exercise. So this market right now probably has a value of around $9–10 billion, and it's predicted to get up to about 27 billion by 2028. You can see that nanoclays are really probably the most important nanofiller class. Automotive and aerospace is a big area. Epoxy resins are one of the areas that are growing fast in terms of the matrix materials that people are using, but polyamides are also very significant already. And just to show you a little more about that, here's the breakdown by type. So you can see the clays are here. Next up is carbon nanotubes, and then we kind of have everything else. The different kinds of matrix materials people like to use, polyamide and polyethylene are quite popular. And those are anticipated to grow further, and you see epoxies next, and then a little bit of other stuff. And then finally, in terms of application areas, you can see that again, automotive and aerospace, and then packaging. Those are probably the two big ones. A little bit in electronics and electricals, that's probably where the epoxies come in, and then a few other things. So to sum up then, nanocomposites are badly described by our usual theorists for composites because they are dominated by interfacial behavior. We can avoid the trade-offs of conventional filled systems if the system is compatible thermodynamically and we process it correctly. And okay, I say clays here, that goes for any nanocomposite you like. Some key features well, you get rapid intercalation. This is specific to the clays, but it refers to the diffusion of the clays, the polymer in between the clay layers. You tend to smear out TG. There's a lot of arguments over whether TG changes. I would argue it doesn't really change that much. You just sort of broaden it. And if you do see a big change in TG, then it's probably something else going on. And you get big changes in crystalline microstructures for sure. This is always going to happen in any semi-crystalline system. Some of your systems are going to be good, definitely not all of them. But nonetheless, I would argue that this is really one of the best examples of a high volume product of the so-called nanotechnology era. There were a lot of discussions about nanotechnology, but this stuff is actually used and in very large quantities, as you can see from that market data I presented just a moment ago. So that's my talk on a quick introduction to nanocomposites. If you want to know more, if you'd like to ask questions, I'm happy to answer them. And as you can anticipate, you could probably get me talking about this for a very long time. So no
Thank
problem.
you. Thank you,
You're
Daniel. Thank you,
Mhm.
Daniel, for your presentation. And yes, if you from the audience have questions, please post them in the Q&A box. We'll try to answer them as soon as possible. Then I will ask Professor Bikiaris to share the presentation. And in the meantime, I would like to say hi to Professor Triantafillidis from the Aristotelic University, who joined us for this discussion. He will not present, but he will intervene in the discussion later. So, Professor Bikiaris, the floor is yours.
Okay, thank you very much, Giulio. I would like to welcome all the participants to this training of BIOMAC projects. And Daniel has done a very interesting introduction about nanocomposites. And I will try to present some of our case studies in bio-based polymer nanocomposites produced by different techniques. Okay, I will pass all of these signs since Daniel was mentioned, just to say that we can get a lot of advantages using some nano additives, especially in tensile strength. And if we can see here, the tensile strength of carbon nanotubes is huge, 200 gigapascal. So theoretically, we can add for example, 2% of nanotubes and to increase in high density polyethylene and to increase the tensile strength from 35 megapascal to 4,000 megapascal. We know very well that never happens this in reality. And also you can see here that cellulose nanocrystals have also high tensile strength, 5,000 megapascal. And even in this case, when we add 2% of crystal, non-cellulose crystal, we can enhance the mechanical strength of high density polyethylene from 35 to 185 megapascal approximately. But as Daniel said, the key here for enhancement of these properties is the compatibility, which means to have a very fine dispersion of nanoadditives inside in polymer matrix to get some nanocomposites with improved properties. And this is the main problem here. There are many techniques to prepare nanocomposites, like in-situ polymerization. You can see here one of our apparatus that we have here in our lab producing polyester nanocomposites. Solvent evaporation, nanoparticles can be dispersed in a solvent. After sonication, can be mixed with a polymer solution. Altogether would be sonicated, and after solvent evaporation, we can take the composite film. And the most used technique is the melt mixing technique, when at the beginning the nano additive and the polymer can be melt mixed and extruded. Just few cases in melt extrusion, there are many advantages compared to the other two techniques. The melt blending is easier to use than the solution blending because of its simplicity. The two components, as I said, are first naturally mixed and then feed to a mixed device. Master batches, of course, can produce also here. There is economical and time-saving process with low cost, solvent-free technique, continuous manufacturing process, superior mixing, easy to scale up, improved production properties, processes, uniform to the products produced, the ability to make quick changes to the combinations, flexible scheduling, high production speed is applied to an industrial scale, since we have many compounders here like this for the production of nanocomposites via melt extrusion, even though we can have also the paraben mixing. Of course, there are many challenges here, like the efficient mixing of polymer with nanoparticles to avoid agglomerates, high interfacial bonding, fine dispersion, high temperature and shear force that can affect the molecular weight of the polymers. We'll see some example here, and hydrolytic decomposition of some polymers. And the innovation in process monitoring combination with other techniques, especially with 3D printing, injection molding, and reactive blending. I was trying to find some characteristic example of our studies, and this was very difficult since we have in our lab more than 100 published papers in nanocomposites, and I will start with one of our first attempts in nanocomposites using silica nanoparticles aerosol from the GUSA, which is a fume silica nanoparticle with average particle size about 12 nanometers and a high surface area 200 quadrat meters per gram. And also, except this, the GUSA was also produced a surface treated aerosol named R9074, which is hydrophobic one with about the same particle size but lower specific surface area. This is because aerosol contains some silanoid sulfase group and makes it, as you can see here, very hydrophilic, while the other is a hydrophobic material, since some silanoid group have been covered with methylene groups. We tried to produce some nanocomposites with polypropylene. This was one of the first attempts in production of polymer nanocomposites, and you can see here that tensile strength was slightly increased when we added the fume silica without the derivatization with methylene groups, and even though at high silane groups silica nanoparticles, the tensile strength was almost similar to that of polypropylene. In the case that we use the hydrophobic silica, it was a decrease that was not expected since this material is more hydrophobic, so it should be the interface between polypropylene and silica surface would be much better in this case. The same results have been taken using the lower speed, cross head speed, 5 millimeters per minute. And of course, this was found also in elongation and break, where we are using the modified silane dioxide. We have taken again a lower, let's say, elongation and break. And this is because, as we found with transmission electron microscopy, in higher amounts of silica dioxide, some aggregates have been formed. This is very important because the aim always is to have bound layers and to produce the interpenetrating network. When we have high aggregates, large aggregates, this nanocomposite behaves not like a nanocomposite, but as a composite material. Impact strength was increased again in unmodified silica nanoparticles in higher percentage than in the other case. And we know very well that during melt mixing, we can use a reactive extrusion process, and this was applied here using polypropylene containing maleic anhydride. We know that some silanoyl groups have been in the surface of silica nanoparticles, and we found that this can be interact, forming covalent bonds on some hydrogen bonds. This interaction were very good in order to break the agglomerates in lower particle size, and also you can see here that this was passed to tensile strength enhancement. As the amount of the compatibilizer, the polypropylene with maleic anhydride was increased, we have seen that better tensile strength has been taken, even in cases like here in 15% of silica nanoparticles. Young module was also increased, and allocation and break. These findings have been passed in collaboration with Interplast, a company here in Greece producing some tubes for multi-layer pipe tubes for hot water supply. And the title of this invention was multi-layer plastic pipe with enhanced interlayer body and enhanced mechanical properties and low linear Thälmann expansion, which is very important. So as we can see here, 3 different multi-layer plastics consist from 3 different layers have been produced, and in the inner part, silicon nanoparticles or nanoclays have been added. Polypropylene maleic anhydride copolymer was also added here, and we found that a substantial enhancement was in mechanical properties, and also we succeeded to get pipes with low linear thermal expansion, which is very important during heating and cooling of the water passes from inside of the tubes. Okay, another property that can be enhanced is also crystallization. Daniel mentioned that the degree of crystallization is very important to the final properties of nanocomposites, and we have seen that as the amount of nanosilica increases, the crystallization temperature rises to higher temperatures close to the melting point. This is a proof that all these nanoparticles can act as nucleating agent points. And of course, in another study, we prove that thermal properties of all this material have been improved. We have used in these studies hydrophobic polymer like polypropylene or polyethylene, and some nanoparticles that have surface silanoyl reactive group, let's say. But what happens during melt extrusion? We're using polymers that have some bonds like ester amides that can be cleaved during melt extrusion. This was proved in BIOMAC project in collaboration with Creative Nano, producing some bio-based PLA nano-lignin and lignin nanocomposites. We can see here that during melt extrusion, the molecular weight of PLA was reduced by increasing, substantially improved, reduced by increasing the lignin and nano-lignin content in both cases. And this is because lignin and lignin have some partial and secondary hydroxyl groups that could interact with ester groups of PLA, reducing its molecular weight, or from the remaining molecule inside in lignin and nano-lignin, some hydrolyzed macromolecules can be taken. However, even in this case of the reduction of molecular weight, there is a substantial improvement of mechanical properties. Tensile strength you can see here in the case of nano-lignin, because we have seen that we have succeeded to produce some nanoparticles with sizes about 20 nanometers. And that's why we have a better enhancement, higher enhancement mechanical properties and tensile strength of lignin nanocomposites compared with nano-lignin nanocomposites compared with lignin. And of course, the anti-modules was also increased. Okay, but in this case, to avoid the composition hydrolysis interactions, we can use also solvent evaporation. Second one technique, which is used for a special case when we have thermally unstable polymers or hydrolyzable polymers like PLA or AL polyesters, nano additives that can decompose at high temperatures like nanocellulose that we can not apply via melt mixing above 200 to 120 degrees Celsius when we want to prepare membranes, coatings, and of course in medical and biomedical applications, which is very important to avoid the composition of the drugs. There are many advantages of this technique, like several techniques can be used in solvent evaporation, like simple solvent evaporation, spin coating, freeze drying, electrospinning, 3D printing using bioplotter and other printings. And of course, there is a possibility to have some interaction take place during solvent evaporation. Of course, there are many disadvantages, especially the long time that is needed compared to melt mixing, producing nanocomposites, and of course, the solvent recovery and the use, which is very difficult. We have done a lot of studies using phytosand, stars, natural polysaccharides, and also for drug delivery application in polyvinyl alcohol and polyvinyl pyridine. You can see here one example using polyvinyl alcohol, which is very important because it's used in as additional layer in food packaging application in order to reduce further gas and to enhance the gas barrier properties. We want in collaboration with a small company here in Greece producing bottles for carbonated drink to produce some polyvinyl alcohol nanocomposites. And you can see here in dynamic mechanical measurement that we succeed to get some higher mechanical properties. The storage module was enhanced in all nanocomposites, and also here due to the interactions, the hydrogen bonding that form between the hydroxyl group of nanocomposites of polyvinyl alcohol and silanoid sulfase group, the area in tan delta was slightly reduced in nanocomposites by increasing the amount of the used nanosilica. The thermal properties also have been enhanced, substantially enhanced, because the maximum decomposition temperature was shifted to higher temperature. We applied this technique for pharmaceutical application collaboration with a company that we have here in Greece, Pharmaten, SI, and we wanted to use some nanocomposites between polyvinyl pyridine and silica. Both are used extensively as excipients in drug delivery application, and we try in Tibolone and other drugs to see the effect. What we wanted, and we know very well that many nano additives are extensively used in drug delivery application, like nanoclays, silica, gold, silver nanoparticles, mesoporous, and others, because all these have a huge surface area. And so it is better to disperse a drug, especially poor drugs, soluble poor drugs in such huge areas, and to produce some pills in order to enhance the solution properties. According to this study, we have applied international patent in collaboration with Pharmaten, which was sold in another company of about 20 million euros. And this technique, salt evaporation, is also very good, appropriate to produce and to get high dispersion, nano additive dispersion, as in this case that was in collaboration with Trento University of Italy. And we study the effect of multi-wall carbon nanotubes in polyethylene, bio-based polyethylene furanoate polyesters are bio-based polyesters with high interest the last years due to much higher mechanical properties compared with terephthalic polyesters, terephthalate polyesters used for food packaging applications, especially for carbonated drinks. And we found here that by solvent evaporation, we can produce nanocomposites with different carbon nanotubes percentages with enhanced storage modules and also tensile strength, even though that elongation break was slightly reduced. And this is because, as you can see here, by scanning electron microscopy micrographs, there is a fine dispersion of all these carbon nanotubes in site in polymer matrix. And this is very important, as was mentioned also in literature. From this fine dispersion, we can enhance not only the mechanical properties, but also other properties like conductivity, which is very important. So we can see here an example of polystyrene using also single-wall nanotubes that the conductivity of this nanocomposite was substantially enhanced using only 0.2 to 0.05 weight% of carbon nanotubes. But as I said, there are many disadvantages because we need to recover, to remove it, the solvent, and to reuse it. Another technique that we have in our lab was the in situ polymerization, especially in polyesters. And we started 10-15 years ago in production of polyethylene terephthalate silica nanocomposites in collaboration with a company from the United States and Marino Xanthos, our collaborator, the Greek guy in United States, who unfortunately was passed away. And in situ polymerization is also an advanced technique since the dispersion of nanoADT can be in used monomers. In our case here in diols, no extra procedure is needed. The nanocomposite could be produced at the end of reaction. Monomers here can interact with nanofiller surface and producing some covalent bonds, and a finer dispersion of nanofiller can be achieved. Here is the two-step polymerization procedure, transesterification and melt polycondensation. So we can, in the first step, we can add here the nano additive with initial monomers, and we found that after some time, the molecular weight here in solid-state polymerization can be enhanced in lower temperature, much higher than in the other. And this is because at low amount of silica nanoparticles, this can be act as chain extenders, while in higher amounts can act as, let's say, branched materials, branched nanoadditive. You can see here that increasing here the temperature of solid-state polymerization, the insoluble content was increased, but we needed to enhance the melt strength because this company in the United States want to produce some nanocomposites with high melt strength because they want to produce some foams that would be stable in higher temperature, higher than 200 degrees Celsius. And this paper was published in Macromolecular Rapid Communication, but it was very difficult to convince the reviewers, the evaluators, that some covalent bonds have been formed between silanoyl groups and the surface of silanoyl groups and polyesters. This was proved in a PhD that was during time in bio-based silica nanocomposites, polybutene succinate and polyethylene succinate. And we found with our PhD student Alexandros that in the case of polybutene succinate, with 0.5 only silica nanoparticles, the molecular weight was substantially improved compared with neat polybutene succinate, and thereafter a slightly decrease was achieved in molecular weight. Completely different was in the case of polyethylene succinate, the behavior of molecular weight increase, and a slightly increase was achieved in all cases. And after 5 weight percentage of silica nano additives, we have succeed to get 90,000 molecular weight. And of course, we can see here in transmission electron microscopy that large agglomerates in all cases, even in 5 weight percentage, have been avoided to be formed. But the most important of this case was that we proved with NMR that some covalent bonds have been formed. You can see here the peak here in this area is a new formed peak that was not in neat polybutene succinate, but only in polybutene succinate silica nanoparticle nanocomposites. And this is the carbon that was covalently bonded with silanoyl groups of silica nanoparticles. And of course, in both cases, there is a substantially increase in mechanical properties, especially the tensile strength at yield point and break point in the case of polyethylene succinate, because the molecular weight, even after 5 weight percentage addition of silica nanoparticle, was substantially improved. We succeed to get 90,000 molecular weights, and you can see here the mechanical tensile strength increase. Of course, elongation, which is very important in order to produce films, both and other final materials, was also substantially improved, about 200%. And of course, young modulus. And the only negative point here in this nanocomposites was that a slight reduction was the enzymatic hydrolysis of this material. And as you can see, by increasing the amount of silica nanoparticle site, a reduction was in enzymatic hydrolysis and mass loss. But even after extending and increasing the time of hydrolysis, at the end, we'll succeed to get some fully decomposed materials. This case was applied in polyesters that have like PLA and silica, that silica can interact and form covalent bonds with PLA. But what will happen when we use another additive that has not a reactive group like biochar? Again, a PhD at running now in our lab in collaboration with the University of Edinburgh. We use biochar here, and we have seen that even though we're adding different percentage of biochar, the molecular weight of nanocomposites is almost similar to that of the initial polybutene succinate. And we have seen that tensile strength in all these cases, again, biochar was added with butanediol and succinic acid at the beginning of reaction in order to produce a nanocomposite by in situ polymerization with melt with a two-step melt polycondensation procedure. And tensile strength was enhanced in all these cases, especially with 2.5 and 5% of biochar. But elongation and break in all these cases was reduced and not increased as in the case of PLA silica polyethylene succinate or polybutene succinate that we have seen previously. The same technique was used also in ring opening polymerization using lactite and functionalized multi-wall carbon nanotube. We functionalized with amino group, and we found that this amino group can interact with ester groups of lactone, starting the polymerization. This was proved here by DSC. The peak of DSC reaction and thermic reaction, and of course, it is clear that as we increase the amount of carbon nanotubes from 0.5 to 5% to 2.5%, this was moved to lower temperature. This is a clear proof that amino groups of functionalized multi-core carbon nanotubes can interact, forming covalently bonds. And of course, this was affected the molecular weight of the final material. It was slightly increased in 0.5 to 1% of functionalized multi-core carbon nanotubes, and only in 100% because in 5% because as we have a higher amount of reactive groups, it is well known that lower molecular weight can be achieved. Of course, in all cases, we have a big, substantial increase in mechanical properties, and especially in elongation and break, and we didn't find the reduction as in the previous case. But also in this case, we have functionalized group, reactive group in the surface of the nano additive. But what happens when we have inactive, let's say, nanoparticles and particles that not have some functional group, like the modified silica nanoparticles, monomerilonite, and neat multi-wall carbon nanotube. In this case, we can see that we have not seen the increase in, again, with in-situ polymerization. We have not seen the high increase in molecular weight polymers like in the previous case, and also tensile strength was only in some cases was slightly increased and was not double as in the case of functionalized multi-wall carbon nanotubes. Of course, allocation break was not affected and slightly increased in modulus. Daniel also mentioned that a big advantage would be of this nanocomposites, the gas barrier enhancing properties, as we found also in polycarbonate silicon nanocomposites, in oxygen, nitrogen, and carbon dioxide. And of course, it is very important to see how all these materials, again in polybutene furanoid based polymers, affect the degree of crystallinity and crystallization rate of the materials. We use in this study 3 different nanoclays, neat nanoclay, and modified with different amino compounds. And we have seen that in all of these cases, there is a reduction, a shift in cold crystallization of polybutene furanoid into lower temperature, which proves the enhancement of crystallization properties, and also because all these acting as nucleating agent, and as the distance between the different layers is higher, this was also the crystallization rate was much higher. And of course, this could be affected also mechanical properties, because the crystallization, the degree of crystallinity is very important. Daniel mentioned also the importance of the bound polymer layer between nano that formed between nano additive and let's say the polymer matrix. As higher is this and stronger, it's better would be the mechanical and the other properties. And of course, because this here nanoparticles could act as could act as nucleating agents. Here the crystalline parts will act. The Ricci amorphic fraction will be much higher than mobile amorphic fraction. And if here between nanoparticles and crystalline phases, some interpenetrating networks are formed, then the mechanical properties and the other will be much better and much higher. Of course, we cannot take the highest advantage of the addition of nanoparticles because the applied stress from to the matrix could be never transferred to the additives, and never the nanoadditives could break, and always the bonds between the matrix that form the bound polymer layer will be broken, which is based on van der Waals reaction, hydrogen bonding, and covalent interaction. As stronger is this interplay here, it's better would be the mechanical properties. And of course, we can use other nanoadditives like silver, zinc oxide, and then to enhance the antibacterial properties of PLA and other polymers. The study here was for film preparation for food packaging application. Just to finish here, the use technique is dependent from the polymer, and the collected nanoadditive mixing is the most common technique. Fine dispersion is the challenge here. Reactive blending can be also used to enhance the mechanical properties to avoid additive of polymer decomposition and hydrolysis. Other technique like solvent evaporation is more appropriate, and in situ polymerization maybe is the more appropriate for fine and nanoadditive dispersion. Covalent bond to be formed when polymer and nanoadditives have some reactive group, and much better mechanical properties can be achieved in this case. That's all from my side. Thank you very much all for your participation. If there are, Giulio, for both me and Daniel, some...
Yeah, thanks, Dimitrios. And so far, there have been no questions. So this is the time for the attendees to post their questions. And I don't know if Professor Triantafillidis wants to add something.
Yeah, sure, Giulio. So first of all, thank you very much, Giulio, for coordinating this and for the great talks from Dimitri and Daniel. Dimitri gave us, I would say, the latest trends to nanocomposites, but Daniel gave us the basic chemistry and brought me back about 20 years ago, in Michigan State. So let me give a couple of general comments. Daniel and Dimitris talked about dispersion. And if we talk about dispersion at the macro scale, of course, we need to consider to match the polarity between the nanofiller and the polymer. So as soon as we match the polarity, the initial, let's say, diffusion of the nano additive would be easier in the bulk polymer. And then we go towards the nanoscale and angstrom scale, and we start thinking about the functional groups on the polymer and on the nanofiller. So if there is some kind of reactivity, as Dimitris just said about the amino groups with some kind of carbonyl group, then we start having strong interfacial interaction, as Daniel said. And why is this important? It is important, of course, to improve the dispersion of the nanofiller. And at the same time, we improve also the load transfer from the polymer to the nanofiller. And of course, we affect the polymer chain mobility. So chemically bonding the nanofiller with the polymer is also very important. And one last comment is about how we select the nanofiller. And we select the nanofiller. Of course, we try to select a compatible nanofiller with the polymer, but our primary aim is to see what application we are aiming at. For example, if the primary application would be a barrier property, then definitely we will go for a layered material, like nanoclays or whatever. And if the primary property, for example, more modern nanofillers like nanolignin is UV blocking and antioxidant properties, we would go for the nanolignin. Or so we need to consider all this, of course, the application, and between the available nanofillers for a specific application, we need to consider polarity matching and interfacial properties with the filler. So thank you very much to both speakers, and we are all at your here at your disposal to answer questions and to help you with the nanocomposite stuff. Thank you very much, Julie.
Thank you. And in the meantime, waiting for some of the attendees to post the last minute questions, I would like to remember that all the training sessions, the training webinars that we have done so far are available on the YouTube channel of BIOMAC, and this will be made available as well later today or in the next days at the latest. And I see that today we have very shy attendees, so maybe they have a clear idea thanks to the clearness of your presentations. And there's in the chat box, okay, they thank all of you for your presentations. And so far, I guess we can conclude this webinar, which has which went beyond 1 hour duration, so the longest one we had so far, and it will not be the last, of course, so you will stay updated on the next activities. And don't remember to check the open call of the BIOMAC project, which is in its last couple of weeks of duration. Then thank to our speakers, and thank you to the attendees for the participation, and we will see you in the next training webinar. Goodbye.
Okay, thank you, Julia, and the participants.
Thanks a lot, folks.
Very nice afternoon. Bye-bye.
Bye.
Take care.